long day after, today I will discuss vector space and subspace of a vector space just as a review. We all of us know what is the vector space. In my previous lecture, I had discussed full topic on vector space. Today I will discuss some more extra topic, more extra example just as a review. We all of us know what is the definition of vector space. Vector space means this 7 property. But to find vector space, only I will say there exists only 2 property, vector addition and scalar multiplication. If these 2 property hold, then that imply this is vector space. We all of us know this is. Actually today I will discuss some more extra concept, more extra example. All of us know complex number, real number, rational number all be vector space. If we consider the complex number, then consider 2 vector x and y. Their sum and their multiplication be always be member of Cn. So Cn is a vector space. We all of us know this part. But here the idea is, here this alpha be the member of field. Alpha be the member of scalar field A. And always vector space defined over the scalar field, because for multiplication this scalar number also need. Complex number is a vector space over real number. Similarly, complex number is vector space over complex number. Complex number is vector space over rational number. But if we consider complex number is a vector space over real number, this means I times the vector 1, 2, 0, 0. In vector multiplication, this multiplication means I, 2i, 0, 0. Here this is vector, but this is scalar number. Since here vector space over the real number, so this is does not belongs to real number. This is the member of complex number. So when the vector space complex number over the field real number, then this type of multiplication does not allowed here. Okay? This type of multiplication would be applicable when complex number is a vector space over the complex number. Otherwise this type of multiplication when over real number, when rational number, this type of multiplication does not allowed. I hope my all viewers have understood. This is actually extra part which I have not defined elaborately in my previous video. This type of concept actually very important for higher study, for deep knowledge of vector space. Okay? Well, consider another type of vector space. A belongs to M cross N matrix. Then the set of a solution X belongs to Rn such that Ax equal to 0. Obviously this set of solution is homogeneous system of equation, we all of us know. And this set of solution actually vector space, because if we consider 2 elements in the vector space, 2 element x and y belongs to this vector space, means obviously since the set is look like Ax equal to 0, that means Ax equal to 0 and Ay equal to 0. We have to prove their sum also belongs to the set. That means A times x plus y, which is actually Ax plus Ay, and since Ax equal to 0 and Ay equal to 0, so 0 plus 0 which is equal to 0. Therefore A times x plus y equal to 0. And since A times x plus y is equal to 0, that means from this expression we can tell x plus y belongs to the vector space. So A times alpha x equal to obviously alpha times x, and since in the set Ax equal to 0, so this is equal to 0, that imply alpha x belongs to the set V. Therefore, since their sum belongs to the set V and their scalar multiplication belongs to the set V, therefore the solution space is a vector space. Have you understood? Actually, this type of example I have defined elaborately in my previous video. Today I have defined this part just as a review. Next, I will discuss our next observation of this lecture, subspace of a vector space. Today I will discuss this topic actually just as a review. Okay? What is the subspace of a vector space? In my previous video, I have defined this part elaborately. Today I will discuss just as a review. Now I will see what is the subspace. We all of us know the subspace. Subspace actually, this is itself a vector space. And definition of subspace is, consider V be a vector space over the field A and let W be a non-empty subset of the vector space V. Then the set W is said to be subspace of the vector space V. That means this set is said to be subspace if this is itself is vector space. And itself is vector space means, consider two arbitrary vector in the set W. Then their sum belongs to W, and if A belongs to W, then alpha times A also belongs to W. This is the definition of vector subspace. There are some example. We all of us know in R2 the subspace are look like 1 alpha times 1 2, where alpha belongs to R. This is actually the line in R2 which is passing through origin and the vector 1 2. This is also subspace because if we consider two vector 1 2 and 4 8, which is equal to 5 10, and 5 10 means actually 5 times 1 2. Obviously this is member of W. Also C times any vector 1 2 also would be belongs to this vector W. So this is the subspace. Another subspace, line passing through origin, which is look like alpha times 1 0 such that alpha belongs to R. This is actually subspace of R2. Another whole space R2 and the set 0 0 who is containing the origin is the subspace of R2. That means this type of set, one line passing through origin, another x-axis or y-axis or whole R2 or trivial space is a subspace of R2. Okay. Now consider the set in R2 W equal to xy belongs to R2 such that xy greater than 0, greater than equal to 0. Obviously this is the upper half plane, but this plane is not subspace of R2. Why this is not subspace of R2? Because consider two vector xy in the space W, but since the space R2 is a vector space, so we can take the scalar alpha which is less than 0. Then alpha times xy would be, the operation would be alpha x comma alpha y, and since alpha is less than 0, therefore alpha x would be less than 0 and alpha y would be less than 0. Therefore this set alpha x comma alpha y does not belongs to W, but I have taken the vector xy from W, but their scalar multiplication does not belongs to W. So upper half plane is not subspace of R2. I hope my all viewers have understood this concept easily. Our next subspace W equal to xy belongs to R2 such that x equal to y plus 2. Obviously this is not be a subspace because subspace means always there exists content 0 0 vector. We all of us know, in my previous video I have seen this part. But here 0 0 does not belongs to this W. Also, if we consider two vector x1 y1 and x2 y2 from the space W, then that imply x1 equal to, since this is member of W, that imply x1 equal to y1 plus 2 and x2 equal to y2 plus 2. Then their sum would be x1 plus x2 equal to y1 plus y2 plus 4. Okay? But since W be a vector space, so their sum always belongs to vector space. Since x1 comma y1 and x2 comma y2 belongs to W and W be a vector space, so their sum x1 plus x2 comma y1 plus y2, obviously this is be the member of W because W be a vector space, but their sum means since the set is x equal to y plus 2, their sum means x1 plus x2 equal to y1 plus y2 plus 2. These two value does not equal. So here this W is not subspace of R2. I hope my all viewers have understood how look like the subspace of R2. Okay? Well, we will consider R3. Obviously R3 is a vector space. Now I will see the subspace of R3. R3 whole space and trivial vector 0 is always be the subspace, and another subspace is, and if we consider the set W equal to set containing the element x00 such that x belongs to R, which is obviously subset of R3, and this type of set means W is a subspace of R3. And next, the set contain W equal to set containing the element xy0 such that xy belongs to R. This type of set also subspace of R3. But if we consider R2, then R2 is not subspace of R3. Why not? Because R3 contain 3 components, but R2 contain 2 components. So R2 is not subset of R3. Okay? Now if we consider W equal to the set containing the element x, y, z such that x, y, z belongs to integer, is this subspace of R3? 0 element always belongs to W. So 2 element which belongs to W, then their sum also would be belongs to W, and their scalar multiplication C times x, y, z. Here, since the original vector space is R3, so if we consider C equal to half, because scalar B belongs to in this vector space, then by property of multiplication, this would be Cx, Cy, Cz. But since C equal to half I have considered, this is does not belongs to subset W. But here I have considered this vector x, y, z from W. But their scalar multiplication does not belongs to W. So W be not subspace of R3. Have you understood? Why I have told you vector space over field, subspace over field. This concept is very important concept. This is not subspace only. Here the original vector space is R3. So this is not the subspace. Next example of subspace, fx. V equal to fx, which is actually fx means all polynomial over the field f. Obviously this is vector space because if we consider two polynomial, then their sum also belongs to this polynomial and their scalar multiplication also belongs to this polynomial. But if we consider one subset W equal to polynomial of degree less than equal to n over the field f, obviously this subset is a subset of fx, where fx is all polynomial over the field f. Here W is subspace of fx because here I have considered degree less than equal to n. Sum of two polynomial whose degree less than equal to n, this is always belongs to W, and scalar multiplication of the polynomial whose degree less than equal to n also belongs to W. So W is a vector subspace of the fx. Okay. Next, if we consider W equal to xpx, where px belongs to fx, obviously this means such polynomial whose root is equal to the 0, that means f0 equal to 0. This is also subspace of fx because if we consider two polynomial such type px and qx, since here the set is xpx, that means consider two polynomial xpx and xqx which belongs to W, then their sum means x times px plus qx. Also this is be the member of W, and alpha x times px be the member of W. So W is a subspace of the vector space fx. I hope my all viewers have understood how look like the subspace of polynomial ring with the field f. And in polynomial, if we consider P2R, which is polynomial of degree 2, this is subspace of P3R, means polynomial of degree 3. Polynomial of degree 2 with real field always be subspace of polynomial of degree 3 with real field, because if we consider two polynomial of degree 2, then their sum also would be polynomial of degree 2 and their scalar multiplication would be polynomial of degree 2 if we consider any polynomial of degree 2. So polynomial of degree 2, since this is subset of polynomial of degree 3, so polynomial of degree 2 over the field R, this is subspace of polynomial of degree 3 over the field R. Notice, in polynomial, lower degree always subspace of higher degree, but R2 is not subspace of R3. But when the vector space is polynomial, then P2R, subspace of P3R. Similarly, P3R subspace of P4R. So, PKR is a subspace of PLR where L greater than equal to K. I will see the new type of subspace when the vector space is polynomial. See, set of all even polynomial with a real field always be subspace. This proof is very easy proof. We have to prove set of all even polynomial is a subspace of P of R. For this, consider two polynomial Px and Qx. Then their sum also would be belongs to this space. Consider Hx equal to Px plus Qx. Then H of minus x equal to P of minus x plus Q of minus x. And given P of minus x equal to P of x, just put the value. And Q of minus x equal to Qx. And Px plus Qx equal to Hx. Therefore, I have got H of minus x equal to Hx. So, Ax belongs to set of all even polynomial. We have to prove their scalar multiplication also belongs to this space. For this, consider Hx equal to c times Px, where c is a scalar and Px be any even polynomial. Then H of minus x equal to c times P of minus x, and P of minus x is equal to nothing but P of x. Therefore, this is equal to c times P of x, and c times P of x equal to actually H of x. Therefore, I have got their scalar multiplication also belongs to the set and their sum also belongs to the set. So, set of all even polynomial be the subspace of set of polynomial. Okay? I will see different type of subspace when the vector space is metric space. First, fixed one matrix A equal to 1, 2, 3, 4 such that W equal to AX such that X equal to R2. We have to prove this subset be a subspace. Why? Take two elements B and C belongs to W such that B equal to x1 and C equal to AX2, where for some x1, x2 belongs to R2. Then B plus C equal to A times x1 plus x2. And A times x1 plus x2. Obviously, this would be belongs to R2. And CB any scalar CB equal to AC x1, and obviously this would be belongs to W. So, if we fixed any matrix A, the solution W equal to AX such that X belongs to R2, this type of solution actually subspace of R2. Okay? OL. See, which of the following set is a subspace of MNR? First, A belongs to MNR such that determinant of A equal to 0. Second, A belongs to MNR such that trace of A equal to 0. Third, A belongs to MNR such that rank of A equal to 1. Fourth, A belongs to MNR such that A is symmetric matrix. Which of the following is a subspace of MNR? First, for this, consider two matrix whose determinant is equal to 0. A equal to 1, 0, 0 and B equal to 0, 0, 0, 0, 0, 0, 1. Obviously, these two matrix belongs to W because determinant of A and B equal to 0, but their sum A plus B equal to 1, 0, 0, 1. This determinant of A plus B is equal to 1. Therefore, their sum does not belongs to the set W. So, W is not a subspace. That means option 1 is a wrong option. And option 2 imply A belongs to MNR such that trace of A equal to 0. Trace of A equal to 0. This is obviously subspace because consider two matrix AB which belongs to the space W. That means if AB belongs to W, that imply trace of A equal to 0 and trace of B equal to 0. Then trace of A plus B by the property of trace, this is equal to trace of A plus trace of B, which is equal to 0 plus 0, which is equal to 0. That means I have got trace of A plus B equal to 0. That implies A plus B belongs to W. Similarly, trace of CA means C times trace of A. Since trace of A equal to 0, that means C times 0 equal to 0. That means CA belongs to W. Therefore, I have got A plus B belongs to W and CA belongs to W. So, trace of A is a subspace of MNR. That means option 2 is a right option. Option 3, the set MNR such that rank of A equal to 1. This is be not subspace because rank of A equal to here 1. That means this set does not contain the null vector 0. So, this is subspace. This is not subspace of MNR. And option 4 A is symmetric matrix. Obviously, this is subspace because null matrix always symmetric matrix and sum of two symmetric matrix always symmetric and scalar multiplication of symmetric matrix is always symmetric matrix. So, option 4 is a right option. When A is symmetric matrix, then this is subspace of MNR. I hope my all viewers have understood how look like the subspace of the matrix MNR. I will stop here. In my next video, I will discuss another topic of a vector space. Because few days I will discuss vector space just as a deep knowledge and just as a review. See you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.